Good morning, everyone. I welcome you to this first hydrogen aircraft session. So my name is Peter Schmolgeber. I work at Honora, and I will present our first speaker, Tim Burschyk from DRR. So since 2020, Tim is working at the Institute of System Architecture in Aeronautics at the German Aerospace Center in Hamburg. He conducts research in the field of energy systems integration for unconventional aircraft concepts with a focus on the application of liquid hydrogen fuel system. So Tim, the floor is yours.
All right, yeah, thank you very much. And thanks for the introduction and good morning to everybody. So yeah, in my presentation, I'd like to talk about the global sensitivity analysis of liquid hydrogen storage design parameters for overall aircraft design. So first, a few words about the motivation. I think like everybody tries to get involved to make air travel more sustainable. And one question which arises is, will hydrogen-fueled aircraft be part of the solution? With that, we're facing the challenge that in the assessment of an overall aircraft design, we partly rely on some certain assumptions. And to exemplify this a little, I take the example of the gravimetric efficiency, which is basically an indication of like how efficient hydrogen can be stored in an aircraft weight-wise. And if we take a look at like some publications, we see a wide span. And this is also due to some assumptions we as a community take. So the question I would like to address is what influence do these assumptions have? And to tackle this, we performed a global sensitivity analysis. And it's divided by first the use case. So I'll talk a little bit about the aircraft concept. We like identify some parameters and some hydrogen design aspects. I'll talk about how we brought this together as a design methodology. And then I'll get to the core, the uncertainty quantification framework, where we like did this global sensitivity analysis. And we'll finally talk about the results. But first I started with the use case, the aircraft concept. So this aircraft concept was derived in another project called Exact. And it's a short-range aircraft, so with a range of 1,500 nautical miles, seats 200 passengers, and has a reduced cruise Mach of 0.66 and an estimated entry into service in 2040. Which like brought us to the design features of a turboprop with gas turbines, low wing T-tail, and foldable wingtips. And important for our study is that like the hydrogen design features are that we assumed a vacuum-insulated LH2 tank out of aluminum and a pump-driven fuel feed. And this architecture will not change during the study. And yeah, we take this as the baseline for our global sensitivity analysis. So the second point is the parameter identification of hydrogen design aspects. And yeah, I quite like struggled a bit putting all of this together, but we certainly can address, for example, the aircraft configuration. So the question comes, what is the aircraft power provided with direct combustion or fuel cell systems, the storage location, but another aspect could also be the structure, so attachments, materials, shape, baffles, and also the operation is a key issue. For example, how to do inspection and maintenance. And of course, the systems, which is like a great part of uncertainty, which fuel system components to use for all the different systems. So to conduct an overall aircraft design study, we try to boil down all these different aspects into aspects which we can control a little bit better. And we came up with in total 8 different design parameters. For example, the maximum pressure we allow, or the outer tank diameter, since we have an integration to the rear. And there we have it as a fraction of the width of the fuselage. So summing it up, yeah, we conducted a literature study of aircraft operation, aircraft integration, structure, and fuel system, and we aggregated 8 parameters for overall aircraft design. And we also tried to identify bounds for these parameters. So talked about the aircraft, and the hydrogen system. I'll quickly talk about how everything is integrated. So we integrated all this into a design workflow where subdisciplines are linked together and communicate with a design framework, which is called RCE. There, these different tools are executed, and the tools communicate by a specific data schema, which is called CPEX. There the aircraft is converged. And I'll talk just a little bit more detail about the fuel system design. So we get an initial estimate of the fuel we need, then we size the geometry. This is then an input for the structural sizing, conduct the mass, and finally do a trajectory analysis of the thermodynamic behavior of the fuel. So if our initial fuel gas is reached, and this is then synthesized again and fed back into the overall aircraft design workflow. So with this workflow, we conduct the subsystem sizing and aircraft sizing in one workflow. So each parameter combination results in a converged aircraft design, and we can also consider snowball effects with this approach. With that, the uncertainty quantification framework, which is like key part of the study. So the first thing, which is divided into three, are the input uncertainties. And I already talked a little bit about the parameters of these 8 different parameters. And we tried to find some bounds for these different parameters for our specific architecture and use case. And which is also interesting to see is to identify probability density functions for these different parameters, to link them to how uncertain they are. And therefore we have chosen 2 different approaches of distributions, for example the uniform distribution and the truncated normal distribution. And to make just one example, for the maximum pressure we assumed like 1.5 bar as a minimum and 3.5 bar as a maximum pressure, and the expected values shifted a little bit more to the left since we found more studies which assumed that for this architecture. So the second part of this uncertainty quantification framework is actually the surrogate model. So for global sensitivity analysis, we do a variance-based approach. That's why multiple function evaluation are necessary, and we cannot do it with our workflows, since it would take too much time. So we need to construct a surrogate model. And for that, we're using a tool which is called SMARTY. This actually then conducts the surrogate construction based on the Gaussian process. We're constantly evaluating the error statistics until we find like a good overlay of that the workflow is represented well with respect to the surrogate, so that we can make sure that like our global sensitivity analysis can be performed on the surrogate model exclusively. With that, we take the final step, which is the sampling. So for the sampling, we need to define our problem, our input distributions. We evaluate our model of the surrogate model, and can finally do some sensitivity analysis with different measures, for example, like with scatter plots, sensitivity indices, or box plots. And this is the final step where I come to the results after the whole methodology. So first, I'd like to show a little bit the design space exploration. So right now we see just some scattered results, and we see the results. The gravimetric efficiency of the study is plotted against the delta and block fuel, and like the delta is referring to our baseline from the previous study, which is located somewhere around here. So with taking into account these uncertainty bounds, we can see that the design flow is relatively big in its span. but we can also see a clear dependency of the block fuel on the gravimetric efficiency. Another measure which I took in the study was the measure of volumetric efficiency, which is not as universal as the one for gravimetric efficiency. And yeah, I just defined it here to make it clear. So it's the volume of the fluid divided by the volume of the rear compartment. So it's the rear pressure bulkhead and the aircraft skin of the rear. And we can see what the results look for this. So it's the same plot, volumetric efficiency against the block fuel of the reference. And we can see that the results here are clearly a little bit more scattered, which indicates that the gravimetric efficiency has an higher influence on the block fuel than the volumetric efficiency here. So with that, we're still on the system level, and we can take the plots right now and look a bit about not the scattered results, but the distribution of these. And we can take a look at the total output variance. So again, it's the gravimetric efficiency and the volumetric efficiency. And these box plots show that 50% of the samples are within the box. Except for some outliers, the rest is implemented by the whiskers. And here we can see that the mean value of the gravimetric efficiency here is ranked at about 36%, for example. So taking this total output variance, thanks to the global sensitivity analysis, we can also assign these distributions to the parameters which have a major influence on these output variance. So for example, we can see for the gravimetric efficiency, the sensitivity is highest for the tank mass scaling and the maximum pressure. And for the volumetric efficiency, we can see the insulation thickness and the tank diameter ratio has the most effect within these certain bounds. So with that, we can state that the gravimetric efficiency mean value is 36%, and the volumetric efficiency mean value is 38%. The main efficiencies are insulation thickness and diameter ratio. Now we can take these results from system level to aircraft level and apply different metrics for that. So, for example, here we took as a metric the maximum takeoff mass, the block fuel, and the L/D, and I'll go through it step by step. Here again, it's plotted against the difference to our baseline of the previous study, and we can see that, for example, the mean of the MTOM is a little bit higher. Also, the mean of the block fuel is a little bit higher of the initial assumptions, which were a point solution. The L/D decreased a little bit since we have more wetted area in the rear. So this has this negative effect. And here we can also do the same as before, and we can assign these global sensitivities to the different parameters. So here again, we can see, if we start with the L/D, that all factors which are more involved with the volumetric efficiency, like insulation thickness and tank mass scaling or tank diameter ratio, were more influential, and for MTOM, the ones who were more based on the gravimetric efficiency, like the scaling and the maximum pressure. And we can kind of interpret the block fuel as a result of both, where you can see still that the gravimetric efficiency has the higher influence in total here, with respect to the parameters. So we can conclude at this point that we have the assumptions for the baseline are slightly optimistic. So in our previous study, we deviated 2% against the mean value here. And the trend on the overall aircraft design for this study with these initial architecture is more dominated by the gravimetric efficiency. Yes, and with that, I'd like to conclude and like summarize the study. So, we had like a design which took into account the sizing on subsystem and on aircraft level. We had implemented an uncertainty quantification framework where we identified the input uncertainties with the respective bounds and distributions based on a literature study, constructed a surrogate model, and finally came to the result to show not only a point solution, but rather a distribution of the results. And let me use the final words a bit about to just talk about the global sensitivity analysis. So for us, the variation of input uncertainties results in a design space rather than a point solution, and that increased like the confidence in how we see things and how we can derive the sensitivities. So it's a bit more robust. The global sensitivity analysis also helps to identify influential parameters. So this can be used to prioritize research maybe. Like maybe one remark also is that the results depend on the input parameter, the probability density distribution, and changing that, then also the sensitivity also changes. So it's in this point also a little bit up to the designer to cope with that. And the clear aim for that is to minimize these boundaries to have a higher estimation of where you in the end will be. And as a future application, this could be also implemented for different architectures. What happens if we use different materials, for example, CFRP for tanks, if we have different, not direct combustion, but fuel cells, for example, then these sensitivities would probably change. That would be interesting to have a look at. And of course, to have a look at different aircraft concepts, how would this be scaling for regional or for long range, for example? And with that, I think I'm at the end of my presentation, and I'm happy to answer some questions. Thank you very much.
Right, any questions? Yes.
Thank you. Excellent presentation. The constant reference back to your first study leaves us with a bit of a, we have to go and read the first study now, so
yeah, it's true.
Have some absolute numbers would be useful. But anyway, that was my main point. You talked about the fuel system design, the hydrogen system design, which is a major factor in this. And you show quite a complicated picture of all the elements of that design, but then you seem to only focus on weight of the system, total pressure, and amount of insulation in your final analysis. One factor that's quite important, maybe not so much at very short range, but as you go up in range, is what you're going to do with boil-off of the hydrogen. You did show a flare system. If that's just flare to atmosphere, then that affects your percentage fuel usage over the flight and also contributes to global warming in its own right. So what you do with boil-off, whether you re-liquidize, add extra weight, but maintain a higher fuel fraction, or use it in some useful way on the aircraft so you don't just flare it to the atmosphere. Those are all second-level details, but they become important, particularly as you go up in range.
Yeah. Thanks very much for the comment. Also, I can comment a little bit on that. I showed this graph where many subdisciplines were involved, and we actually take a look at like how the boil-off would evolve during the mission. And since we assume a very good insulation, we don't have like this massive boil-off during the mission, or like non-boil-off during the mission. We have rather to pressurize the tank during that. But of course, you have to design the vent system, and this is not done in complete detail. So what we did is we have like a thermodynamic model of the tank, so that we can estimate of how much have to be vented during the mission, or how much do we have to need to use the liquid hydrogen, heat it up, and pressurize the vessel. So this is included, and this is also included in the block fuel. But yeah, a detailed design of the vent system is not done in this regard. But yeah, thanks very much for the question.
Another question?
Thank you for your presentation. You mentioned you had two functions for the probability density. Could you say again why you have two, and how do you choose between one or the other?
Mm-hmm. Yeah, thanks for the question. This also was a point of discussions within the authors team. The uniform distribution basically assumes that everything is more or less same, equal, uncertain, and if we had very less information on that, we used that. If we have a probability density function like in a Gaussian way, we found more literature study indicating in which direction we probably want to could be going, so that then the bounds are less strong. But yeah, this is certainly something we want to address in the future, how we select these inputs uncertainties better and these probability density functions. Yeah. Thanks.
Dries Verstraete, University of Sydney. Maybe I missed it, but it wasn't clear whether, so your gravimetric efficiency depends on your insulation thickness, on your tank wall thickness. Is that you calculate the gravimetric efficiency afterwards, and how do you ensure when you randomly pick combinations of your distribution, how do you ensure that you have a viable design? Pressure could drop below atmospheric, which means you need to heat, as you mentioned earlier. Your maximum pressure could not be high enough for your flight, depending on the choice of parameters. And maybe I missed it, but could you elaborate a little bit on how you address those issues?
Yeah, thanks. So yeah, since it's a relatively broad study, some aspects could be addressed relatively well, others not really. For example, if you have the variation of the pressure, that's actually is taken care of, but not in terms of we actually designed the system, but in terms of how much fuel would be needed to pressurize or vent. So, but that's a very good point in how to set the bounds that the whole design is valid, since we randomize all these samples. And for example, we discovered, so for some aircraft would be relatively long, so it would certainly come to some restrictions in terms of operation, for example. And this is also one question, how to deal with these sample points. Should we be excluded out of the study? In this case, we did not exclude these studies, although the aircraft would be probably not bought by an aircraft manufacturer like that, because it would cause some issues with operations. And here was the focus more on getting the sensitivities in the first place to see the overall picture, rather than selecting the points which are real. But this is right. How can we make sure with this randomization to pick always the correct points? And yeah, haven't an answer yet how to deal with it exactly with this methodology, but this is absolutely worth considering, and we also thought about doing so. Yeah.
Right, let's thank our speaker for his answers. All right. Now I present to you our next speaker, Alexander Heidebrecht. So he got a degree at TU Braunschweig in aerospace technology, focusing on engine aerodynamics and preliminary aircraft design. Then he spent 9 years at DLR in the Institute of Aerodynamics and Flow Technology with CFD application. Then he moved to Cranfield University for 7 years, working on aerodynamic nacelle designs and developing surrogate models for preliminary design. And since 2021, he working at TU Delft on H2 aircraft design, boundary layer propulsion integration. Last, there is work on thrust and drag accounting for BLI engine. So the floor is yours.
Thank you very much for the introduction. Thanks for everybody for turning up. It seems I know half the people in this room, or at least I recognize their faces. So the title's a handful. So low threshold, hydrogen-powered BLI propulsion. That's a couple of concepts that I'm trying to put into one thing. So background, we need to stop it with the kerosene. That should be self-explanatory. So we're trying to move to hydrogen. What's that going to look like? Here are some examples of what those aircraft are going to look like. And yeah, that's the most important one, of course. The thing they have in common, they're all very, very different. They're going to take ages to develop. They're going to take tons of money to develop. And then we have a chicken and egg and a chicken problem, because which airport is going to prepare the infrastructure to make hydrogen available if they don't know that somebody's going to go and buy it from them? Which airline is going to buy this kind of aircraft if they're not sure that every airport is going to provide them with hydrogen in sufficient quantities, guaranteed, because you don't want to get stuck with those things. They're expensive. So which aircraft manufacturer is going to develop them? That's really expensive. It's going to take a while. That can be resolved, but I don't think we can do it in one go. And there's, of course, a couple of projects. There are hydrogen-powered APUs. There are smaller regional aircrafts with less range where you can start applying these. But what we were thinking about is, isn't it possible to do something that doesn't require us to entirely redesign an aircraft, that does more than a hydrogen APU, that goes to the middle of the market, so put it in airplanes that are actually flying around a lot on all the important airports, but with a manageable effort. And the concept, this is a concept drawing from a group of students who started the whole thing in 2020, is the auxiliary power and propulsion unit. The idea is we're replacing the APU with a small engine that is able to provide about 15% of total thrust. It runs on hydrogen, which means fancy new technology. If it fails, we still have the main engines. You're not going to ground your fleet because of some technical issue. If you don't get hydrogen at some point, you can fall back to kerosene, because that engine can deal with both fuels, which is also fairly advanced technology. It's not currently something that exists, but again, we have some assurance, because if the fancy new technology fails, we can still have the main engine. So the idea is it's reasonably robust, and it's not going to put people in danger. So first, an overview of all the modifications we made to the baseline aircraft. The methods, we did some CFD to work out what the thrust is that we can get from it. First, results, if we regard the APPU as a regular third engine, but then I just talked about safety a lot and failure rates and reliability. So we also had an investigation into that. So what happens if we have to provision for failure? It's going to affect the bottom line, obviously. So very quickly, our reference aircraft is the A321neo, weight version 53, that's 93.5 tons. Things we need to change about it. The HTP needs to move away. We need the space for a hydrogen tank. Then we're also adding a bunch of components to the tail, which weigh about 2 tons, which means we need to, the center of gravity shifts, we need to shift the wing by inserting a few frames or removing them on the other side. This is what that looks like, and that means the tail scrape line is moving backwards. that gives us a little bit of extra space that we can use, and we need to redesign the tail cone anyway, so we can change the aero lines a little to give us a bit more volume. This is what that looks like. You can see we've also inverted the bulkhead, but we do not change the length of the passenger cabin or anything upstream from here. So we're really trying to keep the changes to the rear of the aircraft. This is the hydrogen tank we've added, and here's a little bit of a, I can't barely see it. Here's a small engine with a 4.5 square meter open rotor. Based on CAD geometries, etc., we worked out that we can probably accommodate about 14.5 cubic meters of gross internal volume for the tank. I always like to put a little bit of a margin there to account for real effects, so we're assuming we're actually getting 13.6 gross volume, that is. So usable fuel is accordingly a little less. So, method overview. The baseline underlying method I'm using is, it basically takes all the component masses, efficiencies, etc. as an input, and is able to work out fuel burn for a given mission with a given range. It has all the TSFCs. And then what we do to it is we're adding some modifications. We can compute some of the components, masses, efficiencies, etc. And then that goes into a loop which updates the fuel masses so that we've got nothing left at the end. If needed, we can resize the hydrogen tank or the main engine size, etc., etc. And at the end, we have a modified description of the aircraft and its data takeoff and its mission fuel burn. So some of the models that go into this are, it's clear that if we want to do this, it makes complete sense to also upgrade the main engines because we're producing more thrust at the rear. The new engines can be a bit smaller. Also, if we're talking about the A321, it could be probably due another engine upgrade in the 2030s, so that also makes sense. So I used a tool from Peter Jan Prusmans, which simulates engine cycles with a constraint optimization to get the TSFC of a likely 2035 turbofan as a function of top-of-climb thrust requirement. And this also produces a mass estimate, which the engine's obviously getting a little heavier as well. And the other thing is the hydrogen tank. Following some comments I got 2 years ago at ECAS, we updated the model we had. We were using the plain Brewer model. This one now assumes a double-walled vacuum-insulated tank. Yeah, so we're modeling unusable hydrogen fuel systems as well. And I was hoping to learn today whether this is realistic or not, but well, we'll see about it. The only validation, unfortunately, we have is this. So this is what the Brewer model says in terms of gravimetric efficiency. This is what the people from the Cheetah project found is possible. We're a little below that, which I think is good. So this is tank gravimetric efficiency as a function of usable hydrogen mass. The model, by the way, also takes into account that the tank elongates the bigger it gets because it has to squeeze into the tail cone. So, how do we get the TSFC of our rear-mounted BLI engine? Thrust and drag accounting for these things is notoriously difficult, so we've had to split it. We have some amount of fuel power, that's fuel enthalpy flowing towards the gas turbine, which converts it to shaft power with a given efficiency. Delivers that to the rotor, which has a certain efficiency, which is translated into actuator power, so the power that is actually usefully applied to the air, which then results in a change to net vehicle force. Net vehicle force being the total force over the entire airframe, which is what we want to get to zero when we're flying, at least in steady flight. So that is an approximation of what we could call thrust otherwise. However, the APPU engine core obviously has an intake and a core exhaust as well, so those also have an influence. And there's a third factor, which is we've changed the shape of the tail cone, so that's going to change the fuselage drag as well. All these three things to put together, that is the total effect on the total force balance on the aircraft of installing the APPU unit. And all these three have been separately determined using RANS simulations. Getting to the engine first, this is an engine model in gas turbine. We had 2 different master students who modeled the engine independently and came to a very similar conclusion that 44.5% core efficiency should be achievable. However, they did make some simplifications and idealizations, so I downgraded that to 43 to account for gearboxes, bleeds, etc., that may not have been taken into account, hoping that this is a more conservative estimate. Chris is looking funny. It's fine. We'll just assume that it's roughly correct. CFD. I made a model based on available sketches of the fuselage. We had a reasonable estimate for what the vertical tail plane looks like. Here's a picture of the mesh. I'm not going to go into too much detail. We don't have the time. Here's the stream traces on the surface of the reference tail cone, and then if we apply at cruise conditions, Mach 0.78, and if we then apply the geometry change, this looks a little different. You can see this looks like a vortex starting to roll up, which is not great, and it's causing about 4 drag counts extra drag. I'm not very happy about it. I think this could probably be changed, but we didn't really have the time, so we went with it. Stay pessimistic. Some of the upsweep is necessary though, because we do have to accommodate the open rotor, so that makes it a little constrained in the geometry-wise. So keeping the same flow solution, this is the same thing, just now we're showing the actuator volume of for the open rotor and the stream traces at the blade tips. You can see even at the blade tips up here, the Mach number just barely reaches 0.7. So the boundary layer is actually thick enough to cover most of the rotor. Plus we have increased static pressure at the tail cone, which is very good news for anybody designing this kind of open rotor to fly at these speeds. And now we can start applying some power to it. So we're adding momentum to the flow. You can see how that changes the stream tube. You can see how that changes the downstream Mach number, etc. I could talk for hours on the aerodynamics. I'm going to save you that. We extracted all the net vehicle force impacts for various powers, so we can interpolate depending on what kind of power we can deliver with the rotor. We know what kind of force it's going to cause on the aircraft. Putting all of those things together, we have a delta drag. We have a delta NVF core, which I didn't show you the CFD for. We had a student, Burschyk, who did pretty good work on this and ran some simulations using the same approach and found about 1.1 kilonewtons. The reason being it's a submerged inlet, so we have virtually no ram drag at all. Then we're getting about 7.9 kilonewtons out of the rotor itself. The engine core ETA, I've explained that, and for the propeller we had Daumanjot Barada who did some work on this. His work is unfortunately not published yet, so I can't reference it. He used a relatively simple approach, but I think 0.88 as an efficiency for an open rotor in these situations is not unrealistic. I hope it's pessimistic, but I can't prove it, unfortunately. Putting those things together means we get about 9 kilonewtons of thrust. If you care to do the maths, that's actually the thrust, apparent thrust power. I shouldn't say thrust, it's apparent thrust. The apparent thrust power is actually slightly more than the shaft power we're supplying. That tells us what BLI is good for. And this is about 14.6% of the total thrust of the reference aircraft. So if we put all of those things together, we run the fuel burn analysis. This is where we're getting. So I've normalized everything to the A321neo. On the x-axis, you can see block fuel burn. On the y-axis, block energy use. So that's fuel energy. The different designs you see here, this is one where we only put the APPU engine on, but we don't change the main engines. We keep the LEAP 1A. Here, we upgrade the engines, so that's the V3. So that's still kerosene only. And then this is taking this aircraft, putting an APPU engine on, but not changing the engines, not updating the thrust requirement. And C1 is the one where we're actually resizing everything, and this is the design we would end up with. If we compare them, we can see just adding the APPU engine with nothing else gets us 13% reduction in kerosene burn, but doesn't really do anything to the energy use. If we do the same thing to the upgraded engines, with the upgraded engines, we get the same benefit. So even though the additional efficiency of the APPU engine is less compared to the upgraded engines, which have about 8.9% reduction in fuel burn, the relative benefit still stays the same because we're replacing kerosene with hydrogen, effectively. And then if we're resizing the engines, because the engines are getting smaller, but they're restricted by fan radius, they also become a little lighter and about almost 1% more efficient. That gets us these 1.1% additional reduction in fuel burn. Just quick look at the masses. You can see the new engines are getting a bit heavier, but takeoff mass reduces actually, so thrust requirement reduces. And then if we just add the APPU, it gets quite a bit heavy, and then we're removing some of that. So what I'm finding is takeoff and empty mass dictate dominate the energy use, and the APPU efficiency tells us more about the hydrogen use or the thrust share that we can provide. So this is the nice idealized view, assuming that the APPU engine is just as reliable as any kerosene engine. However, we know they might not be because kerosene engines took quite a few decades to get there. And so the first generation of hydrogen engines may not be just as reliable. I will trust that they don't explode, but they may fail a bit more often. So we might not want to trust them with our lives in case one of the main engines has already failed. And so the question is, if we can save some development time, cost, ultimately purchase cost obviously as well, would it be worth providing for some failure scenarios? Would it be worth making the main engines a little bigger, carrying a bit more kerosene just to be safe that we can deal with some of the failures? And that's what the next part of the investigation is about. So here's a sizing mission matrix. C1 is the one you've already seen, where we assume everything always works normal. The opposite is C6, where we're assuming that the APPU engine and the hydrogen system can fail at takeoff, and we will still be able to fly wherever we wanted to fly. So we basically treat them as dead weight, as you would with an APU. The ones in between, if you see something in the diversion line, this says we don't trust the hydrogen system to be available during the diversion, so we must be able to divert on kerosene. This one says we need to be able to divert without the APPU engine entirely. We assume the rotor is feathered, but it's not producing any thrust. We need to be able to do that as well. And then these ones, so this is actually safety. These ones are more operational safety. So these mean if the hydrogen fails, we can still fly to where we wanted to go. We will never have to divert because of a failure, which is of course a higher demand to make. The way this study was run is we're assuming the same APPU engine for all of them, the same maximum size hydrogen tank, and we're adapting the thrust settings for the APPU so that all the usable hydrogen gets used up. We're adapting the main engines, obviously, because the thrust requirement changes, the mass, etc. changes. And of course, then the kerosene amount at takeoff is defined by these missions as well. However, if we're analyzing actual fuel burn, we will assume that things work. So these are just emergency provisions, but we'll assume for the fuel burn analysis, we'll assume that everything works normally. And this is what we get. The blue dots represent the new certification configurations. And as you can see, we're gaining. The reason is, if we assume there's no hydrogen that we can use during diversion, there's no use keeping a hydrogen reserve, so we can use it during the main leg. So the APPU engine can stay at a higher throttle setting than it would otherwise in order to burn all the hydrogen. and replace more kerosene. And then the kerosene that we saved by doing that is almost exactly enough to fly the diversion. In fact, well, I'll get to that in a minute. So just summing up the benefits we're getting 9% kerosene reduction by upgrading the existing engines, and then we're getting 15.5% additional reduction in CO2 emissions from adding the APPU engine. That's, I think, a pleasant result to me. So in total, we're saving 23% in CO2 emissions and in kerosene burn. A little bit more discussion. Well, I've already mentioned, well, in the C2, C3 case, we're not relying on hydrogen for the diversion, so we don't need to use it. Another, just the masters with 12 kilogram kerosene extra is needed for these, so you won't notice. The other thing to notice is C2, C3, C4, C5, they're almost equal. Reason being, the APPU engine only supplies 15% of the thrust, and it's the difference between them is whether or not the APPU engine is used during the diversion, which is also only a very small part of the whole thing, so it makes very little difference. What we can assume, what we can see, of course, is that C4, C5, C6, they're a lot more expensive in terms of energy and kerosene as well, because we need to carry enough kerosene to fly the entire mission. And that's not even used if we don't, if that doesn't come to pass. So, last scenario, if we fly on kerosene, it's actually not that terrible. I'm running out of time, so I'm just going to be very quick. It costs us 1% extra kerosene. So if with the APPU engine, you turn up to an airport, there's no hydrogen available, you'll pay 1% premium on the kerosene you would have been using if you didn't have the APPU engine. At all other cases, at all other times, you can gain 15, also you lose 15.5% emissions. Summarizing, 23% reduction in CO2 emissions. We like that compared to just 9% for engine upgrade alone. We didn't investigate what happens on shorter routes, but you can save even more because the APPU engine can just run on full tilt. We have enough hydrogen available, so we can save even more. A very nice outcome is if we have modestly reduced assumptions about reliability, we can save even more because we can use all the hydrogen directly. That's also great. So we don't even have to pay for the privilege of doing this. Total takeoff mass is reduced a little, so we could actually take more kerosene and fly longer. We haven't investigated the range that would be possible this way, but there's another benefit. And then we can use the APPU engine on the ground to produce power, so no more soot emissions on ground. We can probably taxi on hydrogen. I think airport operators are going to also like this. So there are more benefits that we haven't been able to investigate yet, but I would quite like to. And I think I probably need to stop. So I'll just leave you on this slide. This is just the outlook. Thank you very much. And feel free.
Right, question for Alexander?
I have a question concerning, did you consider all the effects concerning the change in tailplane arrangement, like the cross for the vertical tail plus horizontal plane, so the increase in mass and aerodynamics, and also you were mentioning that you moved the horizontal plane, but I have the impression that the volume that will be available in the tail cone due to you have to maintain all the frames to attach the vertical tail plane and also all the systems like the hydraulic system. And
yes.
So, and in addition, you have removed the APPU, the original APPU,
yeah.
but you are placing there the tank plus a gas turbine engine. So You have also the engine.
Yeah, okay, those were a few questions.
And the last question is, I think what will kill this configuration will be the noise. If you know P-180 aircraft, which is placing a propeller just behind a wing, you have now the propeller behind fuselage plus tailplane.
So
imagine the noise of this.
I'll try and remember your questions in order. The tailplane on the A321 is oversized because it's large enough for an A319, which have a much shorter fuselage. So a preliminary calculation finds we can actually save about 200 kilograms by converting to a cruciform. Also on a cruciform tailplane, the HTP is not stuck in the fuselage boundary layer. So it's a little more effective, so you can deal with a little less area than otherwise. So we think there's a reduction. We currently have a master thesis going on investigating that in more detail. In terms of the mechanical integration, the last slide that was there and no longer visible showed a structure model. So the tank is actually occupying much of what would have been occupied by the HTP trim mechanism. So the space is there. The aircraft overall gets about 30 centimeters longer. 70. And yeah, we do have a concept where some of the loads are routed through the vertical tailplane, enough so that if you remove the tank, it'll be able to hold the rear in place. But otherwise, you still have, so during normal operations, you either have the regular tail cone structure outside of the tank, or we're also investigating the possibility of an integral tank with the structures group in Delft, who are interested in crash-resistant hydrogen tanks. So we're having a look at that, and it seems like there is a valid solution, where you put the stiffeners for the outer tank shell on the outside of that shell, and then they also provide some spacing to the environment. There was another question, but I forgot it. Noise. I can't comment much on noise. We have some people doing propeller design at noise. Well, yeah, a transonic propulsor has to have strongly swept blades, which is good for noise. There are some companies who want to sell open rotors for transonic operations up to Mach 0.8, who say that it is entirely possible to stay within regular noise regulations. I'm not the expert on acoustics. I'm doing aerodynamics and aircraft design and a few things, and I've learned a lot about hydrogen tanks, but I can't quite. Sorry? With a wake interaction. Yeah. Yeah. The VTP, yes. Yeah. Yeah, we haven't. Well, some of the things I'd really love to investigate is the full payload range diagram and off-design operations, because crosswind with a BLI rotor can get interesting, gusts can get interesting, etc., etc. We have not quite looked at that. I think there are ways to deal with them. One thing is, for example, so some of the VTP wake is going to be swallowed by the core intake. That's a pretty cool concept. I'd like to present that as well, but it merits its own presentation, so I'm not going to explain too much.
One short question, basically one question, not three. No? All right, let's thank our speaker one more time. All right, we're done with this session, so I see you later on after lunch for the hydrogen aircraft session number 2. Thank you.